What up, pre-calculus students? We got transformations, lots of transformations, so many transformations, including horizontal dilations. So it's sometimes better to just look at points. And you guys know the definitions of your translations, of your transformations. So what we could do is like use those definitions, use what we know to know how we're going to adjust the points that we can see. This is it's a very good strategy when dealing with transformations. So, for example, my first transformation is h of 2x plus 3. What I'm going to do is understand what the 2x does, what the 2 does, and what the 3 does. And then I'm going to take these points and manipulate them here. Okay. Now, what we talked about in class, what I tried to get through to your head, is like when you're working inside your function, when you're doing your transformations, it's opposite of your expectations, opposite of what you're going to think is happening, and opposite in the order of operations as well. And it affects your x's. Outside your function, normal, expected, affects your y's. Okay? So if I have h of 2x plus 3, this first one, I know that here, this plus 3 is affecting my y's. I'm going to take my y's here, and I'm going to add 3 to them. Okay? That's one thing I'm going to do. Now here, 2x, inside, opposite. Now the 2 times the x, you would think, take your x's multiplied by 2. But it's not going to be true. You will dilate your x's by a factor of 1/2, or you will take your x's and you will multiply them by a half. Now, why is this the case? Now, let's think about it. Let's start with -8. Take that x, multiply it by a half, I go -4. Well, if you took -4 and plugged it in, you'd get h of -8, or it's actually f of -8. Well, I know f of -8 is 6. Okay, well, then I would take that 6 and add 3 to it. So this is 6 plus 3, which is 9. Boom, you get your point, -4, 9, just by manipulating your x, manipulating your y, doing it separately. Everything works out. So take your x's, multiply them by a half. Take your y's, add 3 to them. You're good. Wish these are like spread out a little bit. Double check any of them. Like this is where it's like, do you really know what's going on? Well, let's see. Let's take 2. Let's plug it in for x. Let's find h of 2. So this is h of x, which is f of 2x. So if I plug in 2, I get f of 4 plus 3. Well, f of 4, and this is us like composing, this is f understanding inverses, like all of the stuff we've been doing beforehand is helping us with understanding this. F of 4 is 8. If I take that 8 and add 3, I get 11. That checks out. So like we have just transformed our points by separating x's and y's and boom, just like put them together and it works out. So now we can plot our points and you're going to do this on your homework. -4, 9. -2, 11. -1, 7. 0, 5. 1, 7. 2, 11. 4, 7. It is easier than trying to just like look at the graph and just like go from there. And it won't be exact if you do that. We're kind of expecting things to be exact. Okay. This is tricky stuff, but we just did it. Okay. All right. So that's what the graph looks like of my first one, f of 2x plus 3. Let's look at the second question. h of x is 1/2 f of negative x plus 2. Okay. So I got x, f of negative x plus 2 like that in that order. Now, this is where it's like super important. Is there anything else? There's a 1/2. Okay. And this is h of x. Okay. We see three things going on here. We got the 1/2 on the outside. That's going to adjust my y's. What am I going to do? Multiply by a half. These are horizontally dilating, so y's times a half. Do I see anything else on the outside? No. So the first thing I could do is take my y's and multiply by a half if I want to. Boom, done. But let's look at the x's. Let's do it for the first one. 6 goes to 3. Okay? So 6 goes to 3. Now, here's what's going on with the x's. I got this x plus 2. You guys know that on the inside, that adding 2, you'd shift left to. Why? Because it's like a reverse order of operations. Rather, it's an inverse. Okay? We're kind of undoing what's being done. So this plus 2 means left 3, or you take your x's and subtract 2. Okay, cool. Now, this negative, we don't have to worry so much about like doing the opposite, like not multiplying by a third when it's a 3x. We know we have to multiply our x's by -1. Okay. Now, here is the deal. If you do them in two different orders, you get two different answers. Let's look. -8. Let's subtract 2. Let's subtract 2, and then let's take the opposite. If I subtract 2, then take the opposite, I get 10. Okay? Is that right? Or is it better to take the opposite, then subtract 2? Take your x, multiply by -1, then subtract 2. So do we make this 8, and then 8 minus 2 is 6? That's the question. Well, here's how you could check. You can always check by plugging in this input into your function. Okay? So let's say h of 10 equals 1/2 f of negative x 10 plus 2. Well, what I get is -12. I don't know what f of -12 is. So how do I know that it's going to be outputting 6? I know f of -8 is 6, which then times a half is 3. I don't know what f of -12 is. So I made a mistake here. This is wrong. What you find, again, it's like an inverse. It's like you're undoing what's being done. If you had an equation like here, negative x plus 2 equals your b's or your y's, what would be the inverse function? You would take the opposite of the y's first, and then you would subtract 2. Okay? So that's kind of the idea here. We are undoing what's being done, working on the inside. We got to kind of reverse engineer things, reverse map things, just like finding inverses. So take your x, let's multiply it by -1 first, and then let's subtract 2. Opposite of what we think based on parentheses. Okay. Take the opposite of -8 is 8, and then subtract 2, 6. Now, does this work? 6 plus 2 is 8. Make the opposite -8. You get 6 times a half is 3. Works. Okay? So, turns out your x's, the order in which you do it, because it depends on which one comes first, it's important. You need to multiply by -1. Again, you're reverse engineering, and then you're subtracting 2. So this is what you're doing in this order. This is like the inverse of this. Beautiful. -4, 4 minus 2, 2. 8 divided by 2, 4. -2 times -1 is 2. 2 minus 2 is 0. Half 2. 0. -1. It's 0 minus 2, -2. Half 1. 2 times -1 is -2 minus 2, -4. -4 times 2, 2. This is a little bit busy, I'm sorry. 4 times -1 is -4 minus 2 is -6. 8 times a half is 4. 8 times -1 is -8 minus 2 is -10. Half 4 is 2. Okay. Let's start by kind of understanding what's happening. This is a horizontal reflection. This is a horizontal shift. We'd be doing it in that order. Again, inversing, kind of undoing things. This point 8, 4 maps to -10, 2. Okay, now let's again double check. I got to make sure. If I plugged in -10, I got h of -10. Well, this would be like normal order of operations. I would take that -10 and add 2, and I get -8. -8, opposite would be +8. I know what f of +8 is 4. Again, we've been working on function composition and like understanding that. Times a half is 2. Boom, -10. Okay, it works. Everything works. So we can always go back and check. And if you are like doing your quiz, like go back and check instead of just like blindly doing stuff. -6, 4. -4, 2. -2, 1. 0, 2. 2, 4. 6, 3. This is vertically dilating, reflecting over the x-axis, shifting left 2. That order. We reflect over the x-axis, come here. We vertically dilate here. We shift over 2. There you go, right there. Okay? All right. Next equation, we got this G. That's not F, that's G. We got some stuff going on with G. First one, we get J. I honestly don't need this much graph. All my work is happening underneath, so maybe just make these bigger. Oh, that didn't work. There we go. But I'll just get some more space. -1/3 J of 1/2 x plus 1. G of x plus 1. And that's J. Okay. Maybe I'll put it here and I'll say, here's x, here's J. Let me write that down. -1/3 G of 1/2 x. I probably should have done this one. Okay. Now, first things first. What do we got? Boom. Outside affecting my y's. Boom. Outside affecting my y's. Y's go in the normal order in which you see them. Like pretend like the inside of the G is not happening. You'd get your G values, multiply it by a -1/3, and then add 1 to them in that order. So my first understanding is I got a vertical dilation and reflection, dilation of 1/3, a vertical reflection, and a translation up 1. Or I'm taking my Y values, multiply them by -1/3, add 1 in that order. That order is going to always work out. Boom, that's the first one. Now, this guy, again, inside x's, opposite of expectations. What this requires us to do is multiply our x's by 2. We are reverse engineering what we need to have for x's so that when we are multiplying by a half, it maps to the points that we know. So this is telling me that I need to take my x's and multiply them by 2. This is a horizontal dilation by a factor of 2. Horizontal dilation by a factor of 2. This is a vertical dilation by a factor of negative 1/3, just like expected, or it's a vertical dilation by a third and a vertical reflection. This is a vertical shift or vertical translation of 1. Okay, that's it. -8, -4, 0, 4, 8. In order, +2, +3, 1, +1, +2, -2, -1, -1, 0. Boom. Plot those points. You got it. -8, +3, -4, 1, 0, 2, 4, -1, 8, 0. We can see that vertical flip. We can see that vertical dilation, that vertical compression. We can see the horizontal stretch. Double check. Am I sure this is correct? Well, let's double check. Let's take a point. I don't care. Let's take this guy. Let's plug in -4 into J. What's J of -4? Well, that's -1/3 times G of 1/2 times -4 plus 1. This becomes -1/3 times G of -2 plus 1. Oh, I know what G of -2 is. We've worked on this. That should be an F. Okay, sorry, this is G. I undid that. I know what G of -2 is. We worked on this. It's like, boom, points on my function, points on my table. G of -2 is 0. Okay, 0 times -1/3 stays 0 plus 1, I get 1. Works out. Everything kind of maps correctly to what I expect it to be. We're good. Okay, to the last one. Again, this is G. The trickiest one, again, ordering matters, 1/2 x plus 2. This is J of x. All right. Nothing outside of it. There's no change in my y's. J of x is going to have the same y's. But what are the x's that map to those y's? Well, we got two things going on. We got this vertical dilation. Again, it's going to be an inverse. It's the opposite of what you expect. If you thought about 1/2 x plus 2, what are like the values for our x's that will map us to -4, -2, 0, 2, and 4? Well, you would multiply by 2 first, then subtract 2. This is the idea behind this being a horizontal dilation by times 2, taking your x's, multiplying them by 2 first, then horizontal translating them left 2 or subtracting 2 after, because we're undoing what's being done. I want to take my x's, multiply them by 2, and then subtract 2. I'm using like the inverse function to undo, unmap, kind of reverse map. -4 times 2 is -8 minus 2 is -10. Now, right off the bat, I'm checking. If I plug in -10, G of 1/2 times -10 plus 2, I get G of 1/2 times -8. G, a half times -8 is G of -4. G of -4 is 6. I have -10, I got it, okay? This stuff is so tricky, and like I think that I got it now. And the key is like understanding inverses, honestly. which I didn't expect. -2. Multiply by 2, subtract 2. -4 minus 2, -6. If you double checked, it would work out. You'd get -3. No, -4. -4 times -2. G of -2 I know is 0. Boom, -6, 0. It's like we're reverse mapping what are the x's we need to then manipulate to get the x's that we know. And this is our transformations. So, -2, 2, 6. -10, -6. -6, 0. -2, -3. 2, 6. 6, 3. This is a horizontal dilation and a horizontal shift. Okay? Cool. All right. Understanding this manipulation of x's and y's, you can easily understand the domain and range of transform functions. If you know your domain or your x's of your original function, and this is what, given the domain of a function f, these are the domain and range of f. So these are the x's that we can plug in f. These are the y's that are outputted from the function. Here are my transformations. Well, +2, adding 2 to my y's, shifting my y's up 2, times 3. Don't take your x's and multiply by 3. We are reverse mapping. We need to take our x's, divide by 3, so that I can multiply them by 3 to then plug them in and get the points that kind of we know. So this is take your x's and multiply it by 1/3 or divide by 3. Okay? So my new domain and range of my new function is just the manipulation of these x's by 1/3 and the manipulation of these y's by 2. That's it. Okay. These are domain and range of f. What do we got going on? We have a vertical dilation by 4 and a vertical translation by 1. It will be in that order. It makes sense. You take your f values, multiply them by 4, subtract 1. Cool. However, on the inside, you're not going to take your x's multiplied by 1/2. We're going to take the inverse of that. You're going to take your x's, multiply them by 2. Okay, so it's a vertical dilation by a factor 4 and a translation down 1. This is a horizontal dilation by 2. You're gonna have to have bigger x's than multiplied by 1/2 to get other x's. It's just the idea behind the +1, meaning shift left 1. It's the same thing as the inverse. All right, so that means the new domain and range is going to be 0 to 20, and the new range is -12, -13 to 7. Ooh, okay. I'm going to take my y's multiplied by 3 and add 2. Opposite of what we expect. You're going to take your x's. Again, like what are the inputs that you need? What are the x's that you need? Like reverse engineer. What would you do? I would start with my inputs that need to be divided by 2. I'm going to take these x's, divide them by 2 first, and then add 3. That is my reverse engineering. These are like the x's that you need to then map to x's that you know, kind of thing. It's all about inverses. Take your x's, multiply by 1/2, then add 3. This is going to be vertically dilating and then shifting right 3. I mean, vertically dilating, shifting up, horizontally compressing, horizontally dilating by 1/2, and then add 3. So that's it. You can always check too. I'll show you like how we can check. Okay, so -2 times 1/2 is -1 plus 3 is 2. 4 times a half is 2. 2 plus 3 is 5. Negative 2 times 3 is negative 6 plus 2, negative 4. 3 times 3 is 9 plus 2 is 11. Now let's say this function had the original function, xf of x, had the point negative 2, let's call it 4, 3. Okay. What I'm saying is that I would need to plug in 5, and I would get 11. Okay. If I plugged in 5 into G, and this is plug in an x of 5, my G value should be 11. If I plugged in 5, G of 5, I get 3 times f of 2 times 5 minus 3 is 2 plus 2. That becomes f of 4. I told you f of 4 is 3. Great. So f of 4 is 3. 3 times 3 is 9 plus 2 is 11. That checks out. I took my x, multiplied by a half, added 3. Took my y's, multiplied by 3, added 2. Everything worked out. All right, this is fun. Here, vertical dilation by a factor of half like expected. Vertical translation by 2 like expected. But here, horizontal dilation by a factor of a half. Again, inverse. Horizontal translation, left 2, inverse. What are the x's that we need to then be plugged in so that after you add 2, then multiply 5, we kind of undo what is being done. We're taking the inverse by dividing by 5, then subtracting 2. So that's it. Let's work on our domain first. Take your x's, multiply by a fifth. It's negative 2 and negative 2. Negative 2 and 2, and subtract, you get negative 4 and 0. Take your y's, get negative 5 and 5. Add 2, it's negative 3 and 7. You can check, plugging in negative 4, you should get negative 3. If negative 10 plugged in got you negative 10. Like you could do that. Let's try really quick. Let's pretend that f's got the point negative 10, just like the beginning of my domain range. I bet you negative 4 will plot to negative 3 on graph of G. G of negative 4 equals 1 half f of 5 times negative 4 plus 2 plus 2. This is 1 half f of 5 times negative 2 is negative 10. F of negative 10 is negative 10 times half is negative 5 plus 2 is negative 3. Bam! All right. Now this is fun. This is a graph of f. This is a graph of g. This is a graph of h. What's f of g of x? G of x is x plus 2. So f of x plus 2. Takes this graph and shifts it left 2. We need to take our x's and subtract 2. So I'm going to just eyeball it. 0, 6 becomes negative 2, 6. 1, 4 becomes negative 1, 4. 2, 2 becomes 0, 2. 3, 1 becomes 1, 1. 5, 0 becomes 3, 0. G of f of x. Okay. So g of x would be f of x plus 2. That's interesting how that like pops up. It's a little bit interesting. G of f of x would be f of x plus 2. I'm just plugging in f of x where g is. I haven't done this with notation, so that's a little bit interesting. But what does this do? It shifts the y's up 2. So eyeball it. We got 0, 6. We got 0, 8. We got 2, 2, 2, 4. 3, 1, 3, 3. 5, 0, 5, 2. These are fun. These are good questions. And this really is tying nicely with the previous lessons, surprisingly. F of h of x. Okay. So f of h of x. So that becomes f of x over 2, which is the same as 1 half x. What happens here? This is a horizontal dilation. Take your x's, multiply them by 2. Horizontal dilation by a factor of 2. Take your x's, multiply them by 2. 0, 6 stays 0, 6. No horizontal dilation. 2, 2 becomes 4, 2. Does this make sense? If I plug in 4, oh, this is great. F of h of 4. H of 4 is 2. F of 2 is 2. F of h of 4 is 2. This is really nice. I really actually am digging this. 3, 1 becomes 6, 1. 5, 0 becomes 10, 0. And you could double check this. Plug in any point. F of h of 10. H of 10 is 5. F of 5 is 0. F of h of 10 is 0. H of f of x. Okay. This is where we take f of x, plug it into h. What can we do? Well, it's like it would just be f of x instead of just x over 2. That's 1 half times f of x. What is that? A vertical dilation by a factor of a half. Take your y's, multiply them by a half. This is like a really good stuff here. 6 goes down to 3. 2 goes down to 1. 2, 2 goes down to 2, 1. 3, 1 goes to 3 a half. 5, 0 stays 5, 0. What good stuff, huh? Great stuff. All right. G. Taking F. Vertically dilating by a factor of 2. Horizontally by a factor of 4. If I'm horizontally dilating by a factor of 4, that means on the inside I need a 1/4. This is important. Then translating the results up 5 and then left 6. Now, this is where it's important. We are going to take the x and put that in parentheses, and this is left 6. This is always how it's going to end up. Just letting you guys know. We're never going to ask you to translate first and then dilate, because it actually gets really weird because the dilation happens around the y-axis. So like this is a dilation first and then a translation second when you have the parentheses. Kind of haven't written it down, but like that's what it is. And what it is like you start with 1/4 x, but then you replace x with x minus 6. And it's weird if it goes the other way. So we're not going to do it. G is the result of vertically dilating the graph of f by a factor of 2. Vertical is normal, multiplying by y's by 2. Reflecting across the y-axis. The y-axis is the vertical axis, so it's a horizontal reflection, so I need a negative. Translating the graph up 5, left 2. Yikes. Maybe. Okay. All right. First things first, I'm going to do this. Now, it does not matter what we talk about first. Horizontal then vertical, or vertical then horizontal. Either works. Typically, we like to do x's before y's. but like they're independent of one another. So I don't know, do the x's before y's. The 1/3, again, that's the thing that you're going to get rid of first if you're like inversing, if you're undoing, if it's the opposite of what you expect. So we'd have a horizontal dilation by a factor of 3. We are going to shift then right 5. We will then vertically dilate by a factor of 3, and we will shift up 1. I remember putting this problem together. It was just like, whatever, put a bunch of negatives in here. It's so funny. Okay. A horizontal reflection about the y-axis takes care of that negative. A shift right 1 takes care of that negative 1. A vertical reflection over the x-axis takes care of that negative, and then shifting down 1. All right, great. Boom. Y's times 2, x's times a fourth. Undo on the inside, normal on the outside. Inverse on the inside, normal on the outside. All right, y's times 2, 10, 8, 6, 2, 12. X times a fourth, 0, a fourth, a half, 1, 2. Okay. H is equivalent to F horizontally dilated by a factor of 2. If you're horizontally dilating by a factor of 2, inside your equation goes a half. That's important. If you have a half on the inside, you're taking your x's and multiplying by 2. I'm going the other way around. Vertically dilating by a factor of 4, shifting up 5. What's h of 2? Okay, like I'm just going to do it. F of 1 plus 5. F of 1 is 4 times 4 is 16 plus 5 is 21. Okay. J is equivalent to F horizontally dilated by a factor of 1/4. That's taking it by 4. Vertically dilated by a factor of a fourth. Okay, that's a fourth. Vertically shifted down 3. Okay, so there's no horizontal shifting. What is J of 1? All right, I'll figure it out. J of 1 is 1/4 F of 1 minus 3. Okay, I just did it again. I feel like I wanted to use 8 in some of these. Anyways, F of 1 is 4 times a fourth is 1 minus 3 is negative 2. Okay. F of x equals x squared plus 10. Functions g and h can be interpreted as dilations. Find the dilation. That's fun. Well, there's really like 2 options, right? If it's a dilation, you got f of 2x, 2f of x, or the same thing with like halves. Let's see how these play out. If I have f of 2x, I'll have 2x squared plus 10. That becomes 4x squared plus 10.
Please make sure you are with the appropriate teacher for tutoring, or make your way to the vestibules to wait for your ride, please.
If I have 2 times f of x, I have 2 times x squared plus 10, which becomes 2x squared plus 20. So what do I notice? Like a horizontal dilation just changes this and does not change that. So I'm immediately thinking that we got some horizontal dilations going on right here. The vertical dilation changes that and that. And I can see that is changed both. So I'm immediately knowing that this one is like f of x times 1/10. Does that make sense? 1/10 times x squared plus 10. That gives us x squared over 10 plus 1. So this is a situation where this is a vertical dilation of f by a tenth. Now, the 10 doesn't change, but I got this x squared over 9. Well, if I put a 1/3 in here, then I would have 1/3 squared, 1/3 x squared plus 10 is f of 1/3 x. That's what I meant. F of 1/3 x equals 1/9 x squared plus 10. That is h of x. This is a horizontal dilation by a factor of 3. The 1/3 being opposites, inversing horizontal dilation of 3. This one's fun. How do I get a over 5? Well, it's like some constant times x squared will equal 1/5. Square roots, and you got the square roots of 1/5. So I want a 1 over root 5. F of 1 over root 5 x equals 1 over root 5. Again, I'm looking at f here. X quantity squared plus 10. That becomes 1/5 x squared plus 10. This being the same as this, j equals f of 1 over root 5x, which is a horizontal dilation by a factor of root 5. Good stuff. It's compositions, it's inverses, it's undoing, it's reverse mapping, horizontal dilations, horizontal inside, x's, opposite, inverses, outside, regular functions, order of operations, normal, just like we expect. And if we're used to that, we can just manipulate your x's and y's. It's not that bad, but it's tricky. But that's the name of AP Precalculus. All right, Mr. Mester's out.